In the previous video clip, we have learned wave equation and also wave solution in one dimension. In this case, if you consider the wave equation in one dimension, you know that phi it is like an oscillating quantity that we are interested. And in this case, x it represents the axis of the wave propagation, or roughly speaking, we have the wave of the phi quantity that propagating along the x-axis with the propagating speed v. And that is just the meaning of the wave equation. But the question is, when we try to think about what you have learned in M5, for example, you learn about water wave or the sound wave. Definitely we need more axes to describe the motion of the wave, right? The question is, how can we write down wave equation in 2 dimensions or in 3 dimensions? So let's check it out. Actually, it's not so difficult to write down the wave equation in 2 dimensions and in 3 dimensions. But the derivation is quite difficult for you because at least you need to learn about Euler-Lagrange equation or also calculus of variation. But in any way, I think the form is quite intuitive for 2 dimensions or in 3 dimensions. For example, if you want to describe the motion of the wave, we have to use x-axis and y-axis for the description of the wave motion. Definitely, the wave equation for 2 dimensions can be written as a form like this, right? Phi by d y square equal 1 over v square d square phi by dt square. I think the form is quite intuitive. If you need one more axis to describe the motion of the wave, you just add this term. But the right hand side still the same. And also for 3 dimensions, right? The 3 dimensions wave equation can be written as follow as well. Equal 1 over v square d square phi by dt square. I think it's quite intuitive. When you need more axes to describe the motion of the wave, you just add the second derivative of the axis that you are interested into the wave equation. However, when we try to consider this term and try to recognize what you have learned in the introduction to the vector calculus, you know that the right hand side we can use the Laplace operator to simplify this form. And therefore, to simplify this form, if we have to use this notation, I hope that you still remember, we call the Laplace operator. Finally, the general form of the wave equation can be written as a form of the gradient of the quantity. Sorry, it should be phi, and that is the general form of the wave equation, which can be written as a form of the Laplace operator. I think it's quite intuitive, but it's so difficult for you. I mean, for high school student to for the derivation. So, and then it means that if the quantity phi that you are interested, if you want to check whether it is a wave or not, you have 2 ways to check. The first one is you try to check the physical property of the phi quantity. For example, reflection, refraction, interference, and diffraction, something like this. But if the quantity that you are interested can be appear as the form of the mathematical function, and if your mathematical function can satisfy this equation, we can say that the quantity that we are interested can appear as a form of wave. That is our goal for our course, that we have to show that electric field and the magnetic field can appear as a form of wave as well. 5 4 3 2 1 For the wave solution in 2-dimension and 3-dimension, it also quite intuitive as well. For 2-dimensional wave solution, the solution can be written as follows. The phi or the solution of wave equation can be appear as any form of function that contain omega t term, plus minus wave number multiply the motion in x direction, plus minus k multiply the motion in y direction. But in this case, the wave number in x direction and the wave number in y direction might be different, and therefore we have to put the subscript kx and ky for the solution of wave equation in 2-dimension. And also as well, for the wave solution in 3-dimension can be written as any function f that contain omega t term and also contain this term as well, the wave number along x direction, the wave number along y direction, and also wave number along z direction. But it's quite lengthy, and therefore physicists will try to simplify the final form, and the final form can be written as a form of k vector dot product and also r, where r is like a position vector. I think you know well for position vector, but k is like a wave number vector, and the wave number vector can be written as kx, ky, or and kz or kx multiply unit vector in x direction plus ky multiply unit vector in y direction plus kz multiply unit vector in z direction. So now you know the general form of the wave equation and also the general form of the wave solution, right? So the next step, we try to show that electric field and the magnetic field appear as a form of wave. Let's go back to Maxwell equations.